In this video, I'm going to define the decimal numbers by a process, which isn't any more or less valid than defining them by Dedekind cuts. But Dedekind cuts, if you happen to have come across them, aren't very usable in science, engineering, or mathematics in general. Now, the way I'm going to define them by a process as follows. Draw a line in space and arbitrarily label point 0 and 1. By doing that, I'm now going to assign to every point on that line a decimal or a natural, or equivalently a natural number by the following process. Divide the line up into 10 equal increments. Then if I have a point P on the line, that point P will fall in one of these increments. For example, if the point P is here, it falls in the increment 1, 2, 3. So my first decimal number will be 0.3. That's step 1. Then divide that increment into 10 increments, and it will fall in one of those increments, in this case 1, 2, 3, 4, 5. It falls right after the 5th increment. So the second number in my decimal expansion will be 5. That's step 2. So I now can divide that increment again into 10 increments, and let's say P falls in the 7th increment of that. So proceeding by this way, step 1, 2, 3, 4, I eventually get a number of digits which are either finite in case my point P falls on an incremental line, or if it never does, the digits will be countably infinite. So because the digits are countably infinite, which is a result of the definition of the process, the digits will be a natural number by induction, and you can only use induction on a countably infinite number of digits. So the decimals, so therefore, since the digits in each decimal are finite or countably infinite, I can associate a natural number with each decimal, so the decimals in 0, 1 are countable. And notice I can, as I mentioned before, I can do that with any line increment by just simply labeling 0, 1 as a unit distance. That assigns to every point on this line a unique decimal or natural number. And then natural larger numbers would be like 2 plus whatever you got in that increment. Now, I note that each P is uniquely associated with a decimal or natural number, which is the property of completeness. Furthermore, 0.375 can be interpreted as, oh, I didn't do that. So 0.375 can be interpreted as a sum of distances 3 times 1/10 plus 7 times increment of distance, 7 increments of distance each 1 over 100 plus 5 increments of distance each equal to 1 over 1,000 plus and so on. Now, addition, subtraction, multiplication, and division are defined for any n digits of our decimal number, so for all decimals by induction. And again the critical property which makes all addition, subtraction, multiplication, division definable for decimals is the property that the number of digits in the decimal are finite or countably infinite, so that we can apply induction. So we also note that the decimals are obviously ordered. That P is bigger than that P, and the corresponding decimals are ordered accordingly. So all these properties prove that the decimals are real. Now, there's one special case that seems to come up a lot and give rise to a lot of discussion. That is, by convention, And so I'm going to note that by convention, countably infinite decimals equal the points they uniquely define. So if you ask the question, is 0.333 equal to 1/3? By convention, yes. Numerically, no. Thank you.